Hello everyone, I'm Leonardo Bolzonella from TUDelft in the Netherlands. In this video I want to talk about the design and testing of a medium frequency transformer for H2 production in a solid state transformer architecture. The transformer in question is a 25 kilowatt high voltage transformer operating at 1 kHz. The primary side is then excited with 3.6 kilovolt and the secondary side will output 300 amps of current. We chose a core-type transformer with cylindrical windings because this setup best balances the leakage inductance with the current conduction losses. The final design has an efficiency of 98% and a mass below 50 kilograms, making it ideal for scalable SST systems. With the prototype realized, the next step was then to verify the insulation integrity under the operational stresses, and we started with partial discharge. PD is a localized electrical discharge that typically occurs at points where the electric field is intensified, such as the voids, sharp edges, or interfaces between materials. Unlike a full breakdown, PD does not completely bridge the electrodes, but it can gradually degrade the insulation over time. If it is left unchecked, then it can lead to insulation failure, which is why detecting and limiting PD is critical in a high voltage equipment. In this diagram, we can then see the circuit that it used for detecting PD. High voltage AC supply is connected to a test object via a series impedance, which limits the inrush currents and transients. While the load current will flow through the main path, the PD charges will instead flow through this capacitor, which allows then the measuring equipment to detect these charges. And here we can see we set up our test coil in the circuit. The voltage is supplied through this high voltage transformer, through the series impedance and into the test object via this high voltage electrode. The coupling capacitor is then here, and those bushings are added to prevent external PDs being caused by sharp corners in the setup. The applied voltage is first ramped up to an overvoltage level for about 30 seconds, and then maintained at a lower level for 3 minutes. Throughout the whole test, the PD level is monitored, and the test is passed if the PD charge never crosses the 10 picocoulomb threshold. We can see here that indeed this is the case, so we can confirm that the insulation and the fabrication of the coil are functional. Beyond PD, we also push the insulation system to its natural limit to determine its failure point using a breakdown voltage test. This is done on a sacrificial sample of a coil because the coil will not survive this test. The voltage is gradually risen until a flashover occurs. We can see the insulation will fail at about 20 kV, meaning safely above the operating voltage of 3 kV. This confirms the effectiveness of the insulation strategy for the design, ensuring that it will withstand both operational but also overvoltage stresses. Finally, I want to thank IEEE Industrial Electronics Society students and young professionals for supporting this research.